So we'll have a look at some more of this head loss stuff here. So have a look at page 117 in the book. These are these last two problems that we'll have a look at. So the first one here is to find the flow. So what we've got here is we've had, for a lot of the stuff we've been going over, is we've got this open reservoir at 320 feet, a hydrant at 240 feet. Those are the elevations. We need 20 psi in the hydrant, so that's a requirement for pressure called the required residual pressure there. Okay, so there's the elevation at the reservoir, elevation at the hydrant, required pressure at the hydrant. And we have, instead of C100 pipe now, we've got C140 pipe, so a smoother pipe, 8-inch, 920 feet long. We want to find the flow. All right, now we're going to use the table, but we're going to use it here. We're going to kind of put in the information we know about both sides. So at the reservoir, we've got an elevation of 320, no pressure head because it's an open reservoir up there at the top. We're ignoring velocity head, so the total energy at the reservoir is 320 feet. Now at the hydrant, we've got an elevation of 240 feet, 20 psi required. So for the table, we take that 20 psi and we convert it into feet. It's 46.2. So the total, and no velocity head at the hydrant. So the total energy at the hydrant is 286.2. At the reservoir, it's 320. So what you can then do to find the head loss is subtract the two, and that'll tell you the allowable head loss between the reservoir and the hydrant. This is as much head loss as you can have and still maintain the 20 psi residual. So that comes out to be 33.8 feet. Now the pipe is 920 feet long. That's 9.2 100-foot lengths. So if you take the 33.8 and you divide it by 9.2, what you get is the allowable head loss per 100 feet. It's 3.67 feet per 100 feet of length of pipe. All right. Now, the next thing that we would do here would be to have a look at the table, the head loss table. Now we're given that we've got 8-inch pipe here. So we go to the 8-inch table and we're looking for something around 3.67 feet of head loss. It's in between 1,100 and 1,200 gallons per minute somewhere. The 1,100 looks like 3.52 and the 1,200 is 4.14. So it's in between. To be conservative, we could round down and call it 1,100 gallons per minute. Okay, so that's a safe answer, so to speak. Now, that's for C100. Okay, now if the pipe is smoother, if the C is 140, you'll get more flow through the pipe. So the flow that you use on the table is the equivalent flow. So that's 1,100 gallons per minute equivalent flow. Now we have this formula off the formula sheet that tells us that the equivalent flow is the actual flow times 100 over C. So if we solve that formula for the actual flow, the equivalent flow is then multiplied by C over 100. We take the reciprocal of the 100 over C when we want to apply it to the equivalent flow on the other side. Okay. Essentially what we're doing algebraically is we're multiplying both sides of the equation by C over 100. That would cancel out on the right, all this stuff here, and bring the C to over 100 over there to the left. So we got Q actual is Q equivalent times C over 100. That's the relationship. All right. So what we've got here is the equivalent flow that we used on the table was 1,100 gallons per minute. That would hold for C100 pipe. But we're going to factor that by C over 100, 140 over 100, and get 1540. That's the actual flow you could get through the smoother C140 pipe. The 1100 is what you could get through the 100 C100 pipe, but you could get more flow through the smoother pipe. So we take the C100 flow, the 1,100 gallons per minute, and increase it to account for the fact that the pipe's smoother. So we end up multiplying by 140 over 100 and get 1540 gallons per minute for the actual flow. So that's the flow you could get out of this system and still keep the 20 psi residual. All right, the next one, we have the same table set up. What we've got this time, though, is we've got 2,100 gallons per minute. That's the flow that we need to get through the system and we still have to have the 20 psi residual. Now we want to size a pipe, and we've got the same variables here. We've got 920 feet of pipe, C140. Okay, so the table's built in exactly the same way, and we do the same thing with it. We get 320 for the reservoir, a total energy of 286.2 for the hydrant, and the difference is 33.8. Divide that by 9.2, and we get 3.67 feet per 100 feet of allowable head loss. Any more head loss than that, and then our residual will go down too far, okay? Our residual pressure. So that's the highest head loss we can have and still keep the 20 psi residual. Okay, we're given 2,100 gallons per minute here, so what we do is we want to find the equivalent flow to use on the table. So we take the 2,100 gallons per minute, multiply it by 100 over C, and get an equivalent flow of 1,500 gallons per minute. Then we go look at the table, and what we're after here is 1,500 gallons per minute for different pipe sizes. For 8-inch, the head loss for that is 6.25. For 10-inch, the head loss is 2.11. So that's one above and one below our actual allowable head loss. Our maximum allowable head loss is 3.67 feet per 100. So 8-inch won't work. It's got too much head loss. That will drop the pressure too low. It'll drop it below the 20 psi required. So we go up a size, up to 10-inch, which has a head loss of only 2.11. That'll get us the 20 psi required, and actually that'll get us a little bit more pressure because we don't have quite as much head loss as this number here. So we're going to actually have a bit more than the 20 psi. But if 20 psi is required, we can't use 8-inch. It's too much head loss, so we got to go up to the 10-inch size to get the required 20 psi minimum. All right. Now the next one here is minor head losses. And we're skipping ahead a bit. And this is the head loss that you get when you start forcing flow through fittings and valves and different things that you put on pipes. And this is on page 122. So there's an example of what, where you might get some minor head loss. You see that those pipes going all over the place. We got a couple of valves there, it looks like. We've got a bunch of fittings. We got a lot of stuff going on there. So all those fittings and valves are going to cause head loss. So the way we find the head loss associated with fittings and valves, and I'm on page 122 now, is where I'm at, is we find what we call an equivalent length for different things that we're running the water through. So for example, if we've got an 8-inch gate valve that's half closed, and this is written up on page 122, let's find the equivalent length, okay? Now what we're going to do is look at the table on page 123. And for a gate valve half open, the equivalent length, the L over D value, L stands for the length, D is the diameter of the pipe. For a gate valve half open, that's 180. So what we would do is say, okay, L over D is 180. If I multiply both sides of that equation by D, I'll get the L that I need, okay? So if L over D is 180, that means L is 180 times D. Okay, now D is the diameter of the pipe. It's 8-inch, but we want to get that into feet, so we divide it by 12 and get 0.667 feet. So if L over D is 180, if we multiply it by the D of 0.667, we get the equivalent length of a half open gate valve. It's 120 feet. So that what that's telling us in this case is that a half-inch, 8-inch gate valve will have the same head loss as 120 feet of pipe. Okay, so that's this statement right here. So an 8-inch gate valve half open will have the same head loss as 120 feet of 8-inch pipe. So what we'll do next here is we'll go look at the head loss charts. We'll go to 2,000 gallons per minute because that's what we'd like to find next. So that's on page 122. So if we have 2,000 gallons per minute flowing through this gate valve, it's 8-inch. So we'll go here, we'll go to 2,000. And we'll see that that has 10.64 feet of head loss per 100 feet. Okay. Now what we've got is an equivalent length of 120. So we'll take the head loss per 100, the 10.64, and multiply it by 1.2 for the 120. and we'll get the head loss through a half open gate valve. It's 12.77 feet. Okay, so that's the approach. We have a table there on page 123 that gives the L over D values. It's also got some sketches on there to show you what the different fittings might look like for some of those different situations. Okay. Okay, so what's happening here with these minor losses is you're getting turbulence when you make the water go through the fittings, and that causes head loss. Okay, so it's based on the turbulence. All right, let's say we've got C100 and we have this situation right here, and we want to find the total head loss. So we've got 240 gallons per minute, C100. We've got a 6-inch piping system here. So this is on page 124. Okay. Now what you want to do is you just want to work through this. You want to find the equivalent length of each of the fittings. So we got the ordinary outlet, and then we've got the 90-degree standard elbow. So we just want to go to that chart, and we want to find the L over D value for those two fittings. So we've got a standard elbow. L over D is 64. And then we have the ordinary outlet, which has an L over D of 20. Okay, so that's 64 and 20. 20 for the outlet, 64 for the elbow. Now we got 6-inch pipe, which is a diameter of half a foot. So what we would do, we would take L over D, 20, times half a foot. Okay, and we'd get 10 feet. That's for the ordinary outlet. So the deal here is that an ordinary outlet has the same head loss as 10 feet of pipe. You do the same thing with the elbow. You take the L over D, which is 64, multiply it by the diameter in feet. Okay, so the diameter has to be in feet here. So we're saying that 6-inch pipe is equal to 6 over 12 feet, which is half a foot. That's where that half a foot is coming from. Okay. So we're going to take the 64 times half a foot, and that will get us 32 feet. So that gets us our equivalent lengths of pipe in feet, which is what we want. So we're saying that the ordinary outlet has the same head loss as 10 feet of 6-inch pipe, and the elbow has the same head loss as 32 feet of 6-inch pipe. So now I want to find the total equivalent length for the system. I've got 10 feet for the outlet, 8 feet for the first run of pipe, 32 feet for the elbow, and then 10 more feet for the next run of pipe. So I just take those 4 lengths. 2 of them are equivalent lengths for the fittings, the 10 and the 32. The other 2 are actual lengths of pipe, 8 and 10. Add them all up, and I get a total of 60 feet. So this system has the same head loss as 60 feet of pipe. So what I can then do is look for 240 gallons per minute in 6-inch pipe. So I'll come on up here to the head loss chart. 240 gallons per minute in 6-inch pipe. Right there, 0.85. So I'll take that 0.85 feet per 100. 60 feet, so multiply that by 0.6, I get 0.51 feet. Okay, that's the head loss of the water running through that system. Okay, so that's how you find head loss in fittings. You convert to an equivalent length by using that L over D value from the chart. The other thing I'll mention is that the head loss in fittings is due primarily to the forcing the flow through the fitting. So you really don't need to worry so much about the roughness of the fitting, the C value of it. You can pretty much assume C100 for whatever your fitting is, and then just use the equivalent length and go from there. All right, so there we go.